In this video, we will go over concepts from sections 3.3, 3.5, and 3.6. So 3.3 starts with slope. Constant rate of change is slope. It's a numerical measure of the steepness of a line, and it can be found by computing the ratio of the rise to the run. It's usually written with the letter M, and it can be presented as a fraction decimal, or percent. So let's look at some examples here. Virtually, rise is the vertical change and run is horizontal. So in other words, rise is going vertically, run is going horizontally. If we move right or up, we use positive numbers, and if we move left or down, we're using negative numbers. This is the same thing as we do when we're plotting. So let's use the graph to find the slope of the point that passes through the points -3, -2, and 1, -5. And the first thing we'll do is plot the points and draw a line that connects the points. And then we can look at the slope. So if we look at the rise, remember the rise, so the rise to get from this point down to the location of the second point, we're actually going down -3, and our run is +4. So our slope is -3 over -4. Here's a block from your book that actually presents a formula where we look at the difference in the y coordinates of the 2 points, y2 minus y1, divided by x2 minus x1. So here's a numerical formula for you to find the slope of the line that connects 2 points. For each pair of points, find the slope of the line that passes through them by using the slope formula, and draw a sketch of the points and the line connecting them to help you make sense of the slope. So here's the first 2 points. So the first thing we're going to do is plot those points. So 1, 1, we go over, right 1 and up 1, and then we have the point 6, 4, so we go right 6, up 4. And now we want to look at the slope of the line. So the rise here, to get from this point to this point, we're going up 3, and our run is over 5, so our slope is going to be 3 over 5. -3, 5, and 3, -5. So first we plot our points. So we have -3, 5, and then we have 3, -5, and we're going to do the rise over the run. So the rise in this case is actually negative, and if you notice we're going down 10, and our run is +6. So -10 over 6, which is the same thing as -3 over 5. 2, 3, and 5, 3. This is one of the special lines. In this case, the y value is never changing. And the slope of this line, if we notice, there is no rise, it's 0. The run here is 3, so the slope of the line is 0 over 3, or 0. So a horizontal line has a slope equal to 0. Let's try these 2 points. This is a vertical line. Now here we notice that the rise is 2, but the run is 0. So what happens when we try to divide by 0? Undefined. So a vertical line is one of the special lines, and it has a slope that is undefined. And here's a nice little picture of how the slope changes depending on the steepness of the line. So we've got undefined slope here on the verticals. Here we've got the positives. Here we've got the negatives. So let's take a look at an example. A hairstylist is analyzing her profits, which were uneven when she began her business. In the 3rd year, she had an annual profit of $45,000. Then her business began to stabilize, and each year after that, her profit increased by the same amount each year. Currently, she's in her 8th year and has $61,000 in profit. What is her annual profit increase? So we went over 5 years because we went from the 3rd year to the 5th year, so that's 8 years. And the change in her profit was $16,000. So if we take that change, $16,000, which would be the rise, over the run, which is 5 years, she's seeing an annual rate increase in her profit of $3,200. Now, just a little connection with what we learned in Cycle 1. We learned how to look at the change in the y values of a set of points and determine if they showed a relationship that was linear, exponential, or neither. In each set, the x values are consecutive integers like we see here. 1, 2, 3, 4. So the rate of change here in x is constant. It's 1. That would be our run. And here our rise, in this case, is going up by 11 each time. So the slope of the line that connects those points would be 11. So let's take a look at some examples using tables. So we want to know whether or not there's a consistent change here. So let's take a look at it. Going from 2706 to 11.26 is 15.8. What's the change when we go from the 27 to the 42? It's also 15.8. And then when we go from the 3rd number to the 4th number, we also see a change in x of 15.8. Now let's look at the y's. When we go from -11 to -7.6, we see an increase. This is our rise of 3.4. and we go from negative 7.6 to negative 4.2, we also see a change of 3.4. But when we go from negative 4.2 up to negative 1, we see a change here of only 3.2. So this is a non-linear relationship. Remember, for linear, we have to have constant change in both x and y. Let's try this example. We see the change here is going up by 17, up by 17, up by 17, and then the y's, in each case, we're increasing by 5, so we do have a linear relationship, and there's the slope of the line, 5, the rise over the run, 5 over 17. Okay, let's go on to section 3.5, and we're going to talk more about linear relationships. And this is a problem that you'll have in the homework. They're going to have you look at a data table and try to find a pattern, and then use the table to create a graph. So if we look here, we see the x values are going up by 1 each time, and what's happening to the y values? They're actually decreasing by 2 each time. So we can go ahead and fill in the remaining points on the table. So subtract 2 each time, we get negative 1, negative 3, negative 5. And then we want to graph these. And I probably would choose maybe the first 2 points. I don't remember what I chose to graph with here, but 0, 5, so that's the y-intercept. And then I could do the point 1, 3. I could do the point 2, 1, and now I've got the graph of my line. Here's another example. Notice in this one we have fractions, which makes the problem a little bit harder. And so it looks, we can see that x is increasing by 1 each time, but it's a little harder to see what's going on with y. But if I change this number here, where x is 1, if I change that y value to a number with the same denominator as the other fractions on either side, I might begin to see the pattern. So I'm going to keep 2's in the denominator, and what's happening in the numerator? Here we're going from negative 9 to negative 5, which means add 5. Negative 4, add 5 gives me 1. I'm going to add 5 each time for my y in the numerator, and so we can see the pattern now. If I add 5 here, I get 6 over 2, which is 3. Add 5 again, and I get 11 over 2, and add 5 again, and I get 16 over 2, which is 8. And so I can graph this line. I'm going to choose to graph the points with the integer values. It's much easier. So here's the graph of my line. So 1, negative 2, and then I would go to the point 3, 3, and then I can check the point 5, 8 and make sure it's on the graph, and it is. A salesperson has 2 job offers. Company A offers a salary of $270 plus 18% commission on the sales volume, and Company B offers a weekly salary more, but the sales commission is lower. For what dollar sales volume V will the 2 offers result in the same pay? So first we want to write an equation for each pay. So for job number 1, the pay is going to be the base salary, $270, plus 18% of the sales volume. For Company B, the salary should be, and this should also be the same letter, I apologize. We'll say the salary should be here, or pay, $540 plus 9% of the sales volume. Now we want to know when these 2 are going to be equal, when they have the same salary. So we're going to set the first equation equal to the second equation. So we're going to say this portion here must equal this portion if they have the same pay. Subtract 270 from both sides. And then we're going to go and subtract 0.09V from both sides. And then finally divide by 0.09V, and we get a sales volume of 3,000 units. So if we were going to sell 3,000 units, either job would give us the same pay. And then the last section we're covering this week, again, we're talking about graphing linear relationships, slope-intercept form of a line. So we know that the point at which a graph crosses an axis is called an intercept. So in this case, the y-intercept is 0, 4. The x-intercept is negative 2, 0. Notice the x-intercept has a y-coordinate of 0 and the y-intercept has an x-coordinate of 0. Complete this table for the equation and then identify the slope and the intercepts, both intercepts, of this graph. So when I let x equal 0, I can go ahead and solve each one of these. Let me just go back for a second. So I went ahead and I let x equal 0 here, so I get 4y equals 12. I solve for y and I get 3. I let x equal 1, etc., and all the way down, I substitute all these values for x and find the corresponding y. And here's my completed table. So what's the slope going to be? So when I go from, let's go from 0 to 2. So the run is 2, and the rise is 1, so the slope is going to be, actually it's negative, it's going to be negative 1/2. And the y-intercept, x-intercept rather, is 6, 0, and the y-intercept is 0, 3. So the slope-intercept of an equation is written in this form: y equals mx plus b, where m is the slope, b is the y-intercept, and it's actually written as an ordered pair. So for each linear equation, identify the slope and the y-intercept. So the slope here is going to be negative 3. The y-intercept is going to be 0, negative 2. The slope here is going to be 1/2, and the y-intercept is going to be 0, negative 8. Now this is written in an opposite form. We actually just flip it around. It's actually negative x plus 4 rather. So the slope is negative 1, and the y-intercept is 0, 4. A few more. Sometimes the numbers are not integers, so here the slope is going to be negative 6.5, and the y-intercept is 0, 2.5. Now notice on this one, the slope is negative 1/3, but there is no constant out here, so that means the y-intercept must be 0, 0. And lastly, now this is one of those special lines. This is a horizontal line, and so the y-intercept here, the slope is 0, and the y-intercept is going to be 0, 4. Again, this is the variable term, so the slope is going to be negative 2, and the y-intercept is going to be 0, 100. Graph the linear equation y equals negative 5x minus 6 by first plotting points and then using the slope and the y-intercept to graph. So to plot points, we want to choose x values, and we want to choose values that we like, but small integer values are easiest to graph. So let's take negative 1. So if I go back into the equation and I substitute in negative 1 for x, when x is negative 1, I get y equals negative 1, so there's my point. When I let x equal 0, my x term drops out and I get y equals negative 6. And then if I let x equal 1, I come up with y equals negative 11. So there's 3 points I can use to graph. Now technically you only need 2 points to graph, but it's nice to get an additional point and use it as a checkpoint to make sure that you didn't make any mistakes in your calculations. So if I go ahead and graph those 3 points that we just found, here's what it looks like. Now let's graph the equation again, but we want to just use the slope and the y-intercept instead of plotting the points. Notice that the equation is in slope-intercept form, and from that, remember the original equation we had, let me go back for a second. The original equation, just jump back for a second, was right here. Y equals negative 3x, equals negative 5x minus 6. Here's my slope, negative 5, and my y-intercept is 0, negative 6. So my y-intercept 0, negative 6, and then I said my slope was negative 5. So if you notice on here, negative 5 would mean go down 5, and my run would be 1, negative 5 over 1. Or I could go back up, go back 1 and up 5. So you plot the y-intercept first, and then you use the slope as the ratio of the rise over the run, and move down 5 and right 1 from that initial point. And again, there's an example of how that works. So if we start at this point and are going to go down 5 because it's a negative rise and our run is 1. We could also go back here and go negative 1 and a rise of 5 in the opposite direction. For each problem, we use meaningful variables to write a linear function to model the situation. Then interpret the slope and the y-intercept in words. Identify which variable would be on the horizontal and which would be on the vertical axis. Model the cost if you buy an iPod for $200 and download songs for $1.29 each. Okay, so the cost is going to be the initial price of the iPod, $200. But then we have to pay $1.29 for each song that we download. So here's an equation to describe that relationship. The slope here gives us the price per song, $1.29. So each additional song I buy costs $1.29. And the y-intercept, 0, 200, is the cost of the iPod with no songs downloaded. The cost of the songs would be on the x-axis, the horizontal, and the total cost would be on the y-axis or the vertical. Model the weekly salary a salesman earns if his salary is a combination of his base salary and commissions on sales. His base salary is $500 and he makes $50 for each sale. So we can put this together as his salary is $500, his base, plus 50 times n, which is number of sales. So the slope here tells us, the 50 tells us that each additional sale is going to earn him another $50. The y-intercept, which is 0, 500, gives his base salary if he made no sales. The total number of sales n would be on the horizontal or x-axis, and the total salary would be on the vertical or the y-axis. So these three sections together do a nice review of linear relationships, looking at the slope-intercept form, and also revisiting the idea of looking at data in tables to determine if there's a linear relationship.